So Manju has asked me to be very to go slowly in the first 3 days, but he said that on the last day, the gloves can be off. So, so I want to tell you of a few more advanced topics on cover time and evolving sets and cutoff. We'll see how far we get, but let's see. Now I want to. Slideshow. So this is some work done some 5 years ago with Jian Ding, who at the time was a student in Berkeley and now is just yesterday received tenure in Chicago, and James Lee, who's at the University of Washington, about cover time. See, it was done in 2010. It took 3 years to appear, 2013. And some of the open problems we posed there have just been solved both by Jian and by Alex Zhai, who's a student at Stanford. I'll tell you a little bit about that as we go. So this is a topic a little different from mixing, but related. It's a topic of cover times. There are many reasons to be interested in cover time. One of them I mentioned yesterday, because cover time corresponds to mixing time in the lamplighter group. But actually, computer scientists are quite interested in cover times because they are estimates for connectivity algorithms. So often you have some network and you want to find out all the vertices in the network, and what you can do is run a random walk, and you want to ask how long must you run so that you'll be reasonably sure that you visited all the vertices in the network, and so you want some estimates on the tail of the cover time. So I'll be more precise in a moment. So we're going to look at the random walk on a graph. And as we've been doing, and look at local times and hitting times. So these are some nice pictures produced by Raisa de Souza. So this is local times for a random walk run on a large square. I think this is 500 by 500 square, and we run the random walk for a long time, and the colors record how many times we visited every site. And here, on this picture, we ran the random walk for longer, and we run this with periodic boundary conditions. So when it's really on a torus, when the walk exits here, it re-enters there. So it will eventually cover the whole square. So again, here, red is the highest number. Yeah, and on this one, the yellow ones were the last to be visited. So, so on the right, the colors mean something different. They mean how long it took to reach every vertex. This is the hitting times, the empirical rather than the expected hitting times, so the cover time is just the maximum of those empirical hitting times. So HUV is the expected number of steps to hit V starting from U, and it turns out to be useful to symmetrize this quantity. So KUV is the hitting time from U to V, expected hitting time plus expected hitting time from V to U. So this is obviously symmetric. Now, the hitting times themselves, they satisfy a triangle inequality. So if I want to hit, the hitting time from U to V is less than the hitting time from U to W plus hitting time from W to V. But they're not symmetric. Once we symmetrize, we retain the triangle inequality, and so this commute times define a metric. That's useful. And the cover time is the expected time to hit all vertices. That may depend on the starting vertex, so we maximize over the starting vertex. And this is just to give you an idea, the orders of magnitude, so without the constants, of cover times of some graphs, right? So for a path, it takes n squared. A complete graph is n log n. An expander is also n log n. So these are computer scientists who worked this out in the 80s. And so a two-dimensional grid is actually one of the harder graphs to analyze. And up to constant, it was done by Aldous and Zuckerman. So it's n log squared n. Actually, determining the constant took a lot of work, and that's something I worked on with Amir Dembo, Jay Rosen, Ofer Zeytouni. And there's some 4 over pi on the outside. And higher dimensional grids turn out to be easier to analyze. So this gives you some idea of different cover times. Yes?
Why is the two-dimensional grid harder than?
So because this three-dimensional, the infinite three-dimensional grid is transient, then you have less dependence. So what is the method that's used to analyze cover times? We'll see in general, upper bounds tend to be easier. So one way to prove an upper bound, which is to just for each point estimate what's the chance it will take a very long time until it's covered, and just and do a union bound over all of these. And this crude method surprisingly gives you the right answer in many cases. But to prove it gives the right answer, you need a lower bound for the cover time. Lower bounds are hard. How do you prove lower bounds? Well, the naive thing is we want to show that the cover time is at least t. So let's take at least some threshold. So let's take a t below this threshold. And then we want to show that at that time it's uncovered. The graph is likely to not be covered. So how could we do that? One way is to count the number of points that are not yet covered. This is a random variable. We want to show at this time this variable is likely to be positive. So we can easily compute its expectation, but a variable with positive expectation or with large expectation might still be 0 with high probability. So then we want some estimate on the variance of this variable. So we want the estimate of the variance on the number of uncovered points. So this involves the dependence between this point and this point being not yet visited. And in 2 dimensions, there's a lot more correlations between this point being unvisited. There's long-range correlation, so it's much harder to analyze the dependence. In fact, the naive approach I just described doesn't work in 2 dimensions, and one needs to do some more clever truncation, which is quite a long story. Okay, so there are some general bounds. The cover time is, so the complete graph, at least up to a factor going to 1, is the fastest one. So cover time is always at least n log n. Again, this is with the sharp constant. This is surprisingly hard to prove. This was a conjecture of Aldous, proved by a computer scientist Uri Feige. And now, a key tool in analyzing hitting times and cover times is the effective resistance between 2 nodes. So many of you may be familiar with this, but for us, there's a relation between commute times and effective resistances, which can be used. And if you are not familiar with effective resistance, you can think of this as a definition. So in any graph, the commute time between u and v is twice the number of edges times the effective resistance between u and v. In particular, the effective resistance defines a metric. So hitting times are easy to compute. So HUV remembers the expected hitting time. So from any two distinct vertices U and V, if I want to hit V from U, I first have to take at least one step. And after that, I have to average over the W's I could reach the hitting time from W to V. So you have this easy identity just by conditioning on the first step. And these identities, you have them for every U and V, and these are linear equations in these quantities HUV. And it's easy to see this is a system of, it's a regular system of equations. So the hitting times are just the unique solution of this system of equations. So this you can do, right, quite fast, less than n cubed operations if n is the number of vertices, and often a lot less because this is often a sparse system of equations. So hitting times are well understood. And one question which was posed by Aldous and Phil in the 90s is, can we compute cover times quickly and deterministically? So quickly, they mean polynomial time in the size of the graph. And this was a hard problem, so they didn't expect an exact calculation, but can you even estimate them up to a reasonable constant deterministically? So if you're willing to randomize, you can just run the random walk many times. Since cover time is at most n cubed, you can really run until the cover time and average the cover time over many experiments, so you'll get some statistical estimate. And they asked, can you describe a deterministic procedure to estimate the cover times? So the best estimate before our work was by Jeff Kahn, Kim, Lovas, and Vu. And it was up to a log n factor, log n squared. But before telling you about that, I have to tell you about the earlier work of Matthews in '88, who related the cover time to the maximal hitting time. So maximal hitting time is certainly less than the cover time. And what Matthews showed is that this estimate is off by at most a log factor. Let's see, I have. Yes.
The definition of cover time is that the expected value of the time it takes to visit all vertices.
That's right. So it's the maximum over the starting point of the expected time to visit all vertices. Yeah. Okay, so for every starting node, we look at the expected time. It's the maximum of the expectations, not the expected maximum. So maximum over the starting point of the expected time to visit all vertices. Yes, you start from the worst. Yeah, right. So we want the worst case upper bound. Now, of course, in many examples, if the graph is transitive, then all starting nodes are the same. And in general, okay. So here's a sketch of a proof of Matthew's proof. If you haven't seen it, this is a really lovely proof. Matthews was a PhD student of Percy Diaconis when he found this proof in the 80s. So again, the cover time is at most the maximal hitting time multiplied by this series. In fact, you can stop at 1 over n minus 1. And Matthew's proof of this is remarkably short, but really creative. So it's based on a random permutation. So he introduces extra randomness in this proof. So we have some randomness coming from the random walk, and Matthews adds additional randomness by saying, let's consider all the vertices, but in a random permutation. J1 to Jn are all the vertices in the graph, but viewed in a random order. How is this going to come in? So denote by tk the first time that all of J1 to Jk are visited. And Yk is the state at the time tk. So yk is going to be 1 of j1 to jk, but it's not necessarily jk, because remember, the j's are in random order, independent of the walk. So among the vertices j1 to jk are a random permutation. Maybe jk is the starting point of the walk. So maybe jk is visited right from the start. So so tk is the first time all of j1 to jk are visited. So it's very possible, in fact, happens frequently that, say, that the tk plus 1 could equal tk, because because jk plus 1 could have been visited right at the beginning. So okay, so yk is the state at time tk. Now we look at the expectation of tk minus 1 condition on the walk until time tk minus 1 and on these j1 to jk. So what is that? It's so we will get 0 unless jk is really the last vertex among j1 to jk to be visited. If jk is not the last, then, well, we've already visited it, so we get 0. So we have this indicator, and so if it is the last, then we have to go from yk minus 1 to jk. So now these taus are the random hitting times. Now this expected hitting time, okay, we have all this conditioning, but it doesn't matter. It's just a hitting time from, so I'm actually, so here, yeah, so one should still, in the notation here, one should still keep the conditioning. But the point is that we can bound this by the maximal hitting time. So the notation here is, I should keep the conditioning for one more step, but then I could say whatever this quantity is, it's at worst the maximal hitting time. So I can replace this by H max. And then, so really one should replace the conditional expectation here by H max. Then, because H max is a constant, I can then take expectation of both sides here. And the expectation of this conditional expectation just will give me the expectation of the difference, tk minus 1. And this is going to be bounded by H max over k, because the probability that yk is jk is exactly 1 over k. This is because we look at the vertices j1 to jk are themselves in a uniform random permutation. So the chance that jk is the last among them to be visited is exactly 1 over k. So really nice proof, especially that it turns out that in many important examples this bound is sharp. So the Matthews bound is often sharp, though it's often hard to prove that it's sharp. But well, you can see in this proof the extra randomness helps in that this probability we can say is exactly 1 over k. So it's pretty easy to see when you look at the proof where it helps. But to guess initially that this is what you want to do, that's very creative. Okay, so in fact there is a similar lower bound. So the cover time is at we can actually apply a similar argument with a lower bound, but instead of the maximal hitting time, we get the minimal hitting time. So it's really the same argument, you have the minimal hitting time. The problem is the minimal hitting time is typically very short, because for neighbors you typically hit quite quickly. So instead of the minimal hitting time, what already Matthew still observes is if I take any if a random walk is going to cover the whole graph, it's in particular going to cover any subset. So choose a subset of well-separated points in your graph. And for any such subset, observe that, well, in order to cover, I have to cover this subset. Now, if they're well-separated, then the hitting time from any two of these points is going to be quite, quite large. And then, so I can choose whatever subset I want. and then I take the minimal hitting time within the subset, and then the log factor, which was obtained is really the same way as in the upper bound. So this is the Matthews lower bound, and so to be precise, Matthews lower bound is this together with H max. So H max is also part of the lower bound. So you can maximize H max and this quantity. And this gives the Matthews lower bound. And what these authors, KKLV, proved is that when you do the math, so the Matthews upper bound, we said, is sharp up to log n, but it can overestimate by a factor of log n. Like if you have a cycle, the hitting time is order n squared between antipodal points in the cycle, but the cover time is still n squared. So the log n is not needed there at all. So the Matthews upper bound can overestimate by a factor of log n. What they proved is that the Matthews lower bound, which is more sophisticated, it involves itself a maximization here. This one is only off by a log n squared. And now, when you look at this maximum, this is a maximum over an exponential collection of sets. So it's not clear that this is something you can compute in polynomial time. But in fact, you can. So there is some dynamic programming algorithm that can compute this maximum recursively very quickly. So this gives an estimate up to log n squared. Still, the Aldous-Phil problem of estimating up to constant was open.
But models cannot be
what?
more than n. Mod s, that is a log of
Right, right. And
more than n.
that's right.
And still you end up log n squared.
Yeah, this is a sophisticated proof, so it's not something one can guess, on the spot. This took these. Okay. So for the tree is an easy case, and Feige-Zitouni found an approximation in 2009 by recursion on a tree. Now, another natural question that motivated research here involves the blanket time. So when you look at the cover time of a graph, even like look at coupon collector, so that's cover time of the complete graph, and at the cover time, you have the last vertex to be visited is visited only once, and other vertices are visited much more frequently. So Winkler and Zuckerman asked about the blanket time. So the beta blanket time is the time where all the local times are within factor beta of each other. So the local time is the number of visits to a vertex normalized by its degree, because we expect to visit more vertices of high degree, so we normalize by the degree. So asymptotically, all the local times are the same. So the ratio of any two local times will go to 1. That's just from basic convergence theory of Markov chains. But Winkler and Zuckerman asked for a more quantitative measure. How long until all these ratios are going to be within beta of each other? And think of beta equals a half or 2. So that's a random time, and they ask for the expectation of this time. So this is they call the blanket time. So you have kind of a blanket of about uniform thickness spread over your state space. Now, they could analyze the blanket time only in very few examples, like the torus and the complete graph. But based on very few examples, they made the courageous guess, namely that the blanket time in all graphs is within some universal constant that only depends on beta, not on the graph, of the cover time. And this was one of the motivations of KKLV. Jeff Kahn told me they wanted to prove this, and the KKLV argument shows that Winkler and Zuckerman conjecture is true up to a log n squared factor. Okay, what it turns out is that their conjecture is true, but this was proved later. So in order to in order to get the solution both of the Aldous-Field conjecture and the Winkler-Zuckerman conjecture, we had to employ the Gaussian free field. So the Gaussian field is an important Gaussian process, both in the discrete and continuum setting. Here we use it in the discrete setting. And it has many alternative definitions. So one definition is it's a Gaussian process. We normalize it to vanish at some vertex. It won't be important really which one. And then it's defined by this relation that the variance of the difference in heights of the process at any 2 points is the effective resistance between those 2 points. So this characterizes the process. Another characterization is given by the covariance function. So we fix this vertex V0 and consider the random walk killed at V0. So this is right. So this is some finite process, and now I can consider this walk started at X and killed at V0 and measure how many times does it visit Y. You count this number of visits, normalize by the degree of Y, and that gives you the green kernel corresponding to this killed random walk. The green kernel is symmetric because we're in a reversible Markov chain and we normalized correctly. And it's positive definite. That also follows from, green kernels are always positive definite. So it is the covariance of a Gaussian process. And and that Gaussian process is exactly the same Gaussian free field, and there are several other equivalent alternative definitions. These are some pictures of how the field looks just on a square at different resolutions.
That formula there does not give you the second moments of Gx.
It does, because we assume that G at 0, which form?
Okay,
So if you just
for y to be naught.
take y to be v naught, yeah. So this applies for all xy, including v naught. So it does give you the second moments, and hence you see that it gives you the covariances. But okay, it's elementary but not trivial to verify that these two formulations are equivalent. It's well known, but still, when we wrote this in Annals of Math, the referees asked us to include the explanation of why these two are the same. So, our main result is that the cover time is equivalent up to a constant to the number of edges in the graph times the expected maximum of the Gaussian free field squared. And this is also equivalent to the blanket time. This is, as I said, the result from 2010. There are some more recent refinements I'll mention at the end. Okay. Yes.
So if we have a regular graph, then how is the blanket time related to the cover time?
Well, first of all, blanket time is always bigger than the cover time, right? Because you have to, so in the cover you have to visit every vertex at least once. In the blanket, you have to visit all vertices within a fraction beta of each other. So our theorem says that on all graphs, the blanket, if you fix beta, say take beta equals 2, then the blanket time is within a universal constant that just depends on beta of the cover time, whether it's regular or irregular.
If it is regular, then the local time that you have expected.
The local time is just the number of visits to a vertex.
Yes. So then are you saying that then the cover time is just depending on beta that you choose?
No. Again, the cover time is defined, it doesn't have any beta in the definition, right? The cover time is when we visit all vertices. We're saying that the blanket time, fix a beta like 2. So we're saying that the blanket time is not much longer than the cover time. It's just within a constant. So at the cover time, the ratio of the local times is huge. But you just have to weight a constant multiple of the cover time, and all the local times get within a constant of each other. Okay, this is, I think, maybe a bit surprising, but that's. And I want to emphasize, we don't know kind of a direct probabilistic proof of this. The only proof is by finding an analytic estimate for the cover time and then showing that the same analytic estimate also works for the blanket time. So there is no direct probabilistic link. So, okay, I won't have time to give the whole background related, but a little bit of this. So this is conveniently for us, the theory of maxima of Gaussian processes has been analyzed extensively before, and so we could rely on it. So for any Gaussian process, going back to certainly to Kolmogorov, the question of understanding maxima was raised, and this study was refined. I'll tell you some high points of that. And one key observation by Dudley is if I have a Gaussian process defined on any index set, the right way to analyze it is to put the metric on the index set, which is given by the L2 distance between the Gaussian variables. So even if my space originally had some other metric, just ignore that and use the metric coming from the Gaussian process. And so there are many steps along the way, but a high point of this theory is the discovery by Fernique in one direction, and then Talleyrand, who completed the proof that the expected maximum of the Gaussian process can be estimated by a deterministic, a complicated but a deterministic quantity based on partitions of the space. I'll tell you later what it is. So in terms of this Talleyrand gamma 2, one can write our theorem as the cover time is equivalent to the number of edges times this gamma 2. Now, although Talleyrand's definition, which I'll tell you later, involved a huge supremum, which looks like it needs exponential time to calculate, again, we could show that there is a recursive algorithm that would compute it in polynomial time.
So what is gamma 2?
I haven't told you yet. But gamma 2 is a deterministic quantity that Talleyrand showed is equivalent to the cover time up to, I'm sorry, not the cover, equivalent to the maximum of the Gaussian process up to a universal constant. But really what happened was, to us was something different, that as we were studying cover times and looking at the proofs by KKLV that I mentioned, it dawned on us that there is an analogy between the study to the study of the maximum of Gaussian process. And once we realized that, then we could rely on that existing theory. And here are just some hints of the connection. So the cover time is at least the maximum hitting time. And the analog of that in the Gaussian world is that the expected maximum of the Gaussian process is at least the maximum over all the individual variables of their. So the expected maximum squared is at least the maximum. So this square is actually should be. I'm sorry. They're missing parentheses here. The cover time is, Matthew's upper bound tells you that the cover time is at most the maximum times the log n. And you can also, by a union bound the expected maximum of a Gaussian process by root log n times the maximum variance of the individual variables. So just because the Gaussian tail is e to the minus x squared, and the inverse function of that gives you a square root log n. So you get, the standard thing is that if you have n Gaussian variables identically distributed, then their maximum is at most order root log n. So when you square that, you get the same log n as in Matthew's upper bound. And there's also a classical bound in lower bound in Gaussian process, which is an analog of Matthew's lower bound. And these two bounds existed together for some decades before it was realized that they are analogs of each other. But really, for us, the key step was work we did with Jian Ding, Martin Barlow, Asaf Nachmias, where we were upper bounding the cover time by some integral, which only after the paper was completed we realized this was an analog of the classical Dudley integral, which estimates the Gaussian process. So once we saw that analogy, we thought, well, then maybe the analogy extends further to the Fernic-Talagrand bound. Okay. And there are further analogies like the classical Gaussian concentration bound. So this is the Gaussian tail. In the work of Kan, Kim, Lovas, and Wu, they obtained a concentration bounds for difference of local times, which has the same kind of Gaussian tail. So this was another suggestion of the connection. And this is the integral I told you we got in some earlier work, upper bounding the cover time. And it's really a very close analog of the Dudley integral for Gaussian process. I don't have time to go into the details of this, but and then I mentioned the Talagrand bound. Now, this is Talagrand's definition, which is quite complicated, and I don't, unless you've seen it, this is one of the alternative definitions, not the first one he gave, of this gamma 2 functional. You partition a space X into P as a partition. So P of X is the unique element of a partition containing X. Then you look at the sequence of partitions of size 2 to the 2 to the k. And then you take an infimum over all sequences of partitions. So this is a huge infimum. Once you fix the partition, you take sup over X and X. And then you have this sum 2 to the k over 2 diameter of the set. So Talagrand has 3 books where he attempts to explain this and derive consequences of this kind of bound. And in each one, he takes a different point of view. And of course, these books have a lot more information than just these bounds. But a good account focused just on this topic is a book by Marcus and Rosen, which is exactly on Markov processes and Gaussian processes, and gives a very careful exposition.
So
you want to learn more?
It must be dying reasonably fast for you to have that convergent, right?
Right. Yes. But remember, AK has size 2 to the 2 to the k.
Yeah, that way elements, so the space is limited, I see.
Yeah. Okay. I mean, I just want to show you there is some concrete definition. If you look at this, it's not at all clear this is computable in polynomial time, but so I'm going to skip. So Nick and Talagrand is to use chaining. So just a union bound over all the points is too crude because the random variables are correlated. So the idea is you first take points that are well separated and you bound your process at these separated points. These are these gray points. Then you look at points that are still reasonably well separated, but for each of these gray points, we look at this, a cluster of red points near it. And now, once we've bounded the variable at the gray point, we just have to control these differences between the gray and the red. So we make use of the correlation by saying that the gray point and the red point are close by. So instead of bounding the red point all by itself, we just bound its difference from the gray point. And this difference is small because what these distances represent is the standard deviation of these Gaussian variables. And this is just 2 stages of this tree. In general, you have to continue. So next to these red points, you find more points. So you just have build some tree structure on your space. So in Kolmogorov's story, this was just happening in an interval or or a square, and this was something like a binary partition. Then Dudley took this idea and said, let's take a general metric space and take an optimal covering by epsilon balls and use that to define and reduce epsilon and use that to define the nodes of this approximating tree. And then Fernique-Talleyrand said, well, these epsilon balls that are used to cover, they're a good choice, but they might not be the optimal choice. So let's just optimize over all possible ways to choose this tree, which is what that previous definition is about. And at first it looks, well, this is some crazy optimization, but it still turns out to be useful. And then, once you optimize over all these trees, then it turns out to be sharp up to constant. In fact, what Talleyrand told me is that this was in the 70s. Fernique came up with the idea of this upper bound optimizing over all trees, and but he was still pessimistic and thought that this would still not be sharp. So he asked Talleyrand to find a counterexample showing that this bound is not sharp. Talleyrand told me he worked for about a year trying to find the counterexample, and he couldn't. And finally he said, well, maybe there isn't. And then in 3 days he got the proof. But of course, this is 3 days after thinking about the problem for a year from the wrong direction. Final element that we use in the proof is a part of Dynkin isomorphism theory. So many of you who've studied Brownian motion know the Ray-Knight theorem that writes the local time of a Brownian motion as a squared Bessel process. And there is an analog of that in general Markov processes, first discovered by Dynkin. And the most powerful version that we know is due to Eisenbaum, Caspi, Marcus, Rosen, and Xi. And there's an exposition in this book I mentioned of Marcus and Rosen. And what it says is that the local time, so we have, so really to even state this, you have to, given a, okay. So this general isomorphism theory is for general Markov process. I won't go into that generality. In the special case of random walks on graphs, we're going to have to switch to continuous time. But when you switch to continuous time, it doesn't affect the cover time. So so one can do that. And once you switch to continuous time, then LTX is these local times. GX is the Gaussian free field I told you about before. And this is really a special case of this isomorphism theorem, which is quite remarkable. So what it says is you take the local time, you add this half GX squared, so G is the Gaussian free field, and this gives you some random field over your graph. So the local times and the Gaussian process are independent. Okay, so you just add this thing. And this is collection of random variables is equal in loss. So the joint distribution, not just the individual variables, the joint distribution is the same as if you take these Gaussian variables, subtract root 2L, I'll square, take half, and look at all the vertices. Now, what is L? So L is a target local time at the vertex V0. So we fix the vertex V0, which we use to define the Gaussian free field. And we wait till we accumulate local time L in that vertex. So that means till our continuous time chain visits that vertex for a total time of L times the degree of V0.
Locals are used for the Gaussian process, GX, right?
No. So this local time is for the random walk, the continuous time random walk. So it's kind of a strange melange of the random walk and the Gaussian process. But the important thing is on the left you see the local time of the, this is the local time field everywhere. It's kind of normalized to b height L at a specific vertex V0. The Gaussian process is normalized to vanish at that vertex V0. It's independent. So note that, you know, on the right-hand side, it's a process involving just the Gaussian process, no random walk, and this constant L that we prescribed. On the left-hand side, it's this combination.
Capital T is the heating time for the
So,
local time at V not exists.
yes. It's a, So, okay, so this is quite remarkable, and there is, it's been, there's still some mystery surrounding this, because it's, the proofs, there are various proofs, but most of them involve, you know, take joint Laplace transforms of both sides. They can be written as ratios of huge determinants, and that's, you know, takes some theory to develop, and you show that they are the same. So this is a very crude sketch of what you can find in Marcus and in the book of Marcus and Rosen. There are now some other proofs as well. So this theory has been used by Alain Sol-Schnittmann in his study of interlacements. So you can find in his relatively new book another point of view on this proof. And there are a couple of other proofs, but there's no kind of really simple probabilistic explanation of this.
So as L goes to infinity,
Yeah.
the right side is going to grow like L.
So in fact, this is, I'll show this maybe in a minute, what happens when L is large. So maybe, so to emphasize what happens when L is large, that's a natural question. I just, you know, write the big quantities in in boldface. So so what happens when you make this L very large, then and you expand the right-hand side, then this L becomes, you know, the dominant term. This is the remainder of the Gaussian correction on the right-hand side, which is lower order. On the left-hand side, this is this variable local time surface, and this is this Gaussian perturbation. Now, the idea is that when you make the local times large enough, these Gaussian perturbations are really going to be lower order, so you'll be able to conclude that the local time field is uniformly positive. In order to prove a lower bound for the blanket time or the cover time, which is the difficult part, the lower bound, you need the local times not to vanish, and for the blanket time, you need the local times to be large enough. Well, the idea is that just by comparing these two sides, since here the right-hand side is a constant with some Gaussian perturbation, the left-hand side is this unknown local time surface with a Gaussian perturbation. If the local time is large enough compared to the Gaussian perturbation, then we can conclude that the local time is approximately constant, which is what we need for the blanket time.
But in dominant fluctuation, the heating time for this thing is going to have heavy tails.
So the heating,
Time for any level.
you know, we are in a finite graph, so it's a different intuition. So I'm going to skip a lot of the details. You can, again, these papers were published and available on the archive. But I want to say that maybe I'll jump to questions. Sorry, list them in these slides as open questions. But in fact, this has recently been solved. So look at the cover time. So we showed that it's equivalent up to constant to the number of edges times the square of the expected maximum of the Gaussian free field. So we show this up to a universal constant, but then the question is, what can you say about this constant? We had some big bound. From looking at examples, it looked like this constant is, for large graphs, asymptotically 1. So there has to be a caveat. So if you're, when you have a Gaussian process and you look at its maximum, it's possible that the maximum is of the same order as individual variables. That's what happens if you take, say, if you take a random walk on a, if you take a Gaussian random walk for n steps. Then if you look at the maximum, just a standard random walk. So the maximum of the walk is going to be order root n, which is the same as the order of the last variable. Similarly, remember that on a cycle, the cover time is the same order as the maximal heating time. And the same is true on a path. Now, this is not an accident. So given a graph, you can ask, is the heating time the same order as the cover time, or are they different? And that turns out to be the same question, is the maximum of the Gaussian free field on this graph equivalent to the individual variables, or does it have a larger standard deviation? If they are of the same order, then the cover time is not concentrated. But again, a theorem of Aldos says that if the cover time and the heating time are different orders, then the cover time as a random variable is concentrated. This is a theorem of Aldos from around 1990. Conversely, there's a Borel concentration and other concentration in Slepian inequality that tell you that for a Gaussian process, if its maximum is bigger than if its maximum has bigger standard deviation than the individual variables, then the maximum is concentrated. And so it's in the latter case we want to focus. So we think of a sequence of graphs where the cover time over the maximal heating time is going to infinity. So this is not true in the cycle, but it's true in most other graphs you can think of, like in the complete graph, in the torus, and so on. So for such a sequence of graphs, one can expect the ratio here to go to 1. And in the paper with James Lee and Jian Ding, we showed one direction. So we showed the cover time divided by this quantity has a lim sup of at most 1. And we conjectured that this is the limit, but we couldn't prove that. Subsequently, Jian Ding showed that under some assumption, this is true. So he showed it if we have a sequence of graphs of fixed bounded degree, and he also showed it in case of trees. And then just last year, Alex Zhai, a student at Stanford, proved the full conjecture. So this is true in the greatest generality of reversible Markov chains, that as long as the cover time over heating time goes to infinity, then the ratio of these two sides goes to 1. And his proof was based on the ideas I showed you, together with one more great idea, which is, given instead of using the isomorphism theorem on the graph, he used it for so-called the cable process. So given a graph, you can always think of the edges of the graph as kind of line segments. And instead of running, say, a continuous random walk on the graph that jumps discretely from point to point, you can run a Brownian motion on this one-dimensional complex. So this is a Brownian motion. On the line segments connecting vertices, you just run a classical Brownian motion. And when you reach a vertex, when you reach a vertex, you just have to kind of choose each excursion which of the edges coming out you're going to go. What?
And you'll start from where you are.
Yes. So this is the most classical example of this is what's called the Walsh spider. You just have a graph. You have a node and k edges sticking out. and you want to do Brownian motion on this object. So all you have to do is decide, right, each time you reach, so you run a standard Brownian motion, each time you reach here, you have to decide where to go. And this is a little tricky because you reach here, uncountably many times. So, but you can index these by excursions, and then just for each excursion, make an independent choice. So if you want to construct this process, you can first run standard Brownian motion, and now take each of these excursions. You can order them by size, and each excursion, assign it a random direction to go. So anyway, there is a cable process. So if I have any kind of graph, there is this cable process. So I have a general graph, and there's a process that runs Brownian motion here and somehow makes the right decision at the corners. And if you examine the local time of this process, so now it's a diffusion on this kind of structure, and the local time just corresponds to a local time of the discrete random walk, of the discrete space continuous time random walk. And Zhai's method is to use instead the isomorphism theorem, instead of in the discrete set graph as we used it, use it directly for this continuous Gaussian process you get on this. And and now the local time is a continuous process, and he can use this continuity effectively to prove the theorem. So
these excursions, you have to wait for the Brownian motion to go away from zero, because zero is the midpoint of.
Each excursion is from zero, and you just have to partition the excursions to the different directions. Okay, so just the final thing. So this conjecture was proved. Another thing we didn't know is, can you improve the approximation? So using the Talleyrand theory, we could estimate the maximum of a Gaussian process up to a constant. But the Talleyrand theory really loses a constant. It doesn't estimate up to 1 plus epsilon. But Raghu Mecca used different ideas to estimate the maximum of a Gaussian process directly without using the Talleyrand theory up to a factor of 1 plus epsilon. So that's work from a couple of years ago. He is now at UCLA. He did it. He was a postdoc in Princeton. Now he's a faculty at UCLA. So I'll stop here, and this second half of today I'll switch to a cutoff and Ramanujan graphs.